I'm Stephen Parker with NVIDIA. I'm VP and CTO of our professional graphics business, and responsible for a bunch of the technologies that we create for artists, designers, engineers, people building almost anything out of their imagination. So it's my honor today to come talk to you about some of the pieces we have in the way we think about design and what the future of design and manufacturing and filmmaking and all of those interrelated fields. So NVIDIA is one of the pioneers of GPU computing. We coined the term GPU. Been around 20 some odd years, almost 10,000 people, and growing faster every day. We build the GPU. Obviously, you probably know about if you're at SIGGRAPH. We build new artificial intelligence algorithms for self-driving cars. We have a trio of self-driving cars, one of which is named BB-8, and you can probably guess what the other two are named. We build a deep learning supercomputer that's an amazing product if you're doing deep learning, and later in the talk I'll show you a little bit about how we're using that same architecture to do rendering as well. And of course, we're the visualization platform of choice for nearly every movie studio, every nominated Academy Award over the last several years has used our products. And some of the largest supercomputers include 9 of the 10 most energy efficient supercomputers. And it turns out that all of those things are quite related. So GPU computing, the idea of graphics processing and things like that, it was largely motivated by a need of people like yourselves to express their imagination. They wanted to first draw pictures and then simulation, and to be able to generate the beauty that we experience in the world around us turns out to be a very computationally intensive process. Simulating the physics of light, or making a game look beautiful, or making a design look beautiful are all very compute intensive processes. And then more recently, we have been involved in a huge wave of understanding, image understanding, human interface understanding, speech recognition, and that's really computing what we would call human intelligence, right? You can describe what is an image using language that each of us would recognize, rather than bits and bytes or looking for the text around it. And so all of those things are quite interrelated. They're dealing with the world around us, either creating a world that doesn't exist or doesn't exist yet, or understanding a world that does exist. And it turns out that the same architecture is quite powerful for both of those aspects of it. And so we're inspired by this, right? It's the next generation of the world, of understanding the world. The next generation of computing is coming out of these trends. So if we drill a little bit further into people that are really leading the tip of the iceberg on this, there's several trends that emerge. There's the people that ask us for more. They're asking for a lot of things, but there's 4 things in particular that really push us to do something new. So larger data sets, everybody has more and more data, whether they're gathering data or creating data. Somehow there ends up being more of it, and a never-ending deluge of data to create and to process. The second big wave is artificial intelligence. Artificial intelligence had a breakthrough a few years ago, a little over a year and a half ago. A neural network for the first time exceeded human performance on an image recognition task. So it could recognize whether this was a a boat or a flower or a car or a child better, more accurately than a human. And that has driven a huge investment by a lot of really large companies in trying to get information out of the data that we've all been collecting for the last many years. So another huge trend is virtual reality, right? So you've undoubtedly seen the hype in virtual reality, and I'll show you a little bit about why that's hard and why that matters. But it's really, if you were doing virtual reality 10 years ago, you would have come and talked to us. But it would have been a pretty expensive endeavor, not just because of our products, but because of all the displays and other machinery that you needed to get. And so the reason that virtual reality has become even more important today is that it's now practical. It's now, the display technology and interface technology has gotten to a point where suddenly everybody can do it. And that will drive a bunch of new trends and open a bunch of new opportunities for all of us in the very near future. And then, of course, photorealism, something that we've been investing in a while, a number of companies been investing in a while. How do you get the virtual world that you're creating to look exactly like the real world, to a point where you're actually simulating the real world instead of just painting a picture of it? And so today I'm going to talk about 4 elements that kind of mirror those pieces, and then show you what I think is how that's going to play out over the next few years. So the first is simulation, rendering, VR, and AI. And if it's almost like buzzword bingo. There's a lot of people doing one of these. There's even fewer doing 2 of them, and some really crazy people are doing 3 of them together. But but almost all of them have some very common threads that we'll go over at the end. So simulation was one of the first pieces that NVIDIA started getting into when we released CUDA 8-10 years ago. And it's people have been harnessing the power of parallel computing, GPU computing, to simulate all sorts of things. So high order elements for structures, particle methods for high explosives, which is actually research that I did before I joined NVIDIA. Fluid structure interaction, analyzing fluid flow in subways, aerodynamics of vehicles, including motorbikes, particle simulations, and so forth. And people initially adopted GPU computing because it was faster, right? So you got some performance. It was fairly inexpensive, easier than scaling it out to a cluster. But that wasn't the only reason to do it. More recently, the idea is to be able to combine all of these things together to be able to perform an interactive, real-time visualization, simulation, where it's not just about cost to performance, but about fundamentally changing the way that people work. Instead of submitting something overnight and getting back an answer tomorrow, I want the answer right now. I want to make a change and see instantly how that change affects my design. Or if I add something, is it going to make it look better? Is it going to reduce performance and aerodynamics or other things like that? So all sorts of pieces of that are really driving that. And these are all images from partners that are engaged in that space. And then there's others that are pushing what you can understand. The other problem with having more and more data is that it's harder and harder to understand it. And so traditional techniques such as clown colors is what the thing on the left is effectively called, don't really convey the information that you're trying to convey. They break down as you add more and more complexity to it. So using more sophisticated rendering algorithms, using more analysis and other computationally intensive techniques, we're able to convey a better image and a better sense of shape and scale, and in this case, damage. A great example we showed it at our GPU technology conference earlier this year. It's a simulation of a rocket motor. You can imagine that's a popular subject among a handful of companies these days. This is just a massive amount of data, both computationally and visually. And really the only practical way to create a visualization like this is to create it as you're performing the computation. Because there's so much data that you can't really save it all, you can't store it all. So, in situ visualization is becoming increasingly utilized in a lot of those fields. So the second main topic I'll introduce is rendering. And NVIDIA works with a lot of rendering partners, but the main one that we have built ourselves is called Iray. It's been out for several years now. It's entirely from scratch, built from ground up to be a physically based rendering product. It's built into several products. We also have plugins for Max and Maya, other mainstream applications, and this allows you to harness the ability to do real-time photorealistic rendering directly in a viewport. You make a change in design, you immediately see what consequences that might have on the look of it. So this is an example of what it looks like in the wild, I guess. This is a old concrete factory that was in Barcelona somewhere that somebody turned into a loft, office space loft area, and it's a gorgeous rendering. One of the plugs I'll give is if you go down to our booth, you'll actually be able to see that in VR if you ask for the loft space. So. And then, because this is a computationally intensive process, it's not something that just you buy a $20 GPU and it's suddenly infinitely fast. Someday we'll get there. But right now, this is a computationally intensive process. And so we've focused on being able to scale that. So if you have a $20 GPU, you get performance. But if you need more than that, you can tap into other resources, either down the hall or in a data center or so forth. Another important piece of that is once you have a physically based rendering system, you want to be able to express materials. The materials in the world around you are quite rich, right? There's a lot of different types of paint. There's different types of metals. There a shocking number of different kinds of plastic, and all of those look different. And if you're one of the trends that we see is that the visual design of products is becoming more and more important. In addition to, it has to work right, but even fairly simple products often have a design sense that needs to be met. And I think Apple's probably the most famous for that in terms of the iPhone, but that attitude and that mindset is permeating industries of all sorts. So this was the one on the right is a watchmaker that we had at SIGGRAPH last year, who completely designed this watch, and I actually don't remember exactly how much it cost. I just remember it had 6 digits in it. So it was essentially a digital watch that has a mechanical. It was completely analog driven, but a digital readout. So V materials, all sorts of different things, and these V materials are different than just writing a shader, because what we do is we take a physical material and then try to produce a digital replica of that physical material. And so instead of just trying to make it look good, you're trying to make it look right. And so that if you go and build a product, you're not surprised by what it looks like. And that mindset really was really attractive to Honda. They took this to heart and showed at our GPU technology conference about a year and a half ago a full CAD model of one of their cars that had, I don't remember, tens of millions of polygons. It was a full thing, physically based rendering and streaming it from a cluster at 10 frames per second. And of course, whether you actually plan to build it or not, or you'd like to make those designs look beautiful, and physically based rendering is kind of the main way that people interact with renderers today. Another fun project to work with was Harley Davidson. They're a motorcycle manufacturer in the United States. If you're not from here, very considered the old school type of company, but they're really revolutionizing their manufacturing process so that they can build new designs faster and keep up with trends and to serve a diverse customer base. And so they have been using Iray and MDL and V materials to be able to predict what a motorcycle would look like if you built it or repainted it, and in order to, both for internal design reviews as well as showcasing to potential customers. And the way that it works is they make changes in their CAD model, and it is quite seamlessly updated in a physically based rendering system. And again, here's a perfect example where you don't care whether it looks good or not. You want it to look right, and if the rendering looks bad, then you know that the product will look bad as well. And again, at SIGGRAPH a year ago, we actually showed this live, where we thought, okay, well, if that's all true, we have to really prove that it's true, right? And so we had this realer rendered idea where we had two pictures. One, we had the drill physically live with the camera on it, and could you tell the difference between the real drill and the one that's videotaped? And of course, if you were there, the easiest thing to do is wave your hand in front of it, and one of them would have a hand in front of it. But and there's some differences, right? There's some slight modeling differences and things like that. But the point is not that it's exactly the same. But the point is, if you built this based on a rendering, you would not be surprised when it came back, and you would not be surprised about what it looked like. So another big focus in rendering has been mental ray. Mental ray's been in the rendering industry for a long time. It's been used in many movies. It's won an Academy Award. And this year it's better than ever. We have figured out how to accelerate this on the GPU, even though it was designed long before GPUs were ever thought of. We have figured out a way in which we can add a GPU to the workflow, and without making fancy changes on your end, to just accelerate the global illumination process. So it now has the same type of workflow as Iray. You can edit it in the scene, make changes, and see that the results of that directly. So that's a product that'll be out soon. It'll be quite valuable if you're a mental ray user. So VR. VR is the next element. The 4 elements that I wanted to talk about. And in particular, there's all sorts of press about how VR will let you spend more time bonding with your grandmother and things like that. And those are really important topics, social topics, right? And but I think more what we're focusing on is how does that revolutionize the creative process? Can I collaborate with somebody else in a different country? Can I understand a design? Can I simulate a surgery before I actually use a scalpel? Can I communicate how big or small a building is to a potential client? All of those things are becoming even more important, and essentially it's the same idea as that we talked about in simulation and in rendering, that we want to be able to make a prediction of what something's going to look like and not be surprised when we actually build it. So, one of the most valuable things in VR for design is in architecture. It's really challenging for an architect to convey a sense of scale, like how tall is a 9-foot ceiling, or how big does this room feel? And an architect that's trained has that sense that they've developed over time, but their clients don't always have that. They don't understand what the difference between a 9-foot ceiling and an 11-foot ceiling. And so it turns out that virtual reality, especially combined with global illumination and rendering, you're kind of getting hints where I'm going to take this, are able to help convey that sense of scale. And it's also, virtual reality just enables some more natural interaction methods and allows us to collaborate with others quite a bit more efficiently. But it turns out that it's not that easy. It's not just simple as putting a headset on. Virtual reality, the accepted minimum frame rate is about 90 frames per second. And instead of creating a single 1080p image at 30 frames per second, which you would typically think of as pretty good for for a CAD model or things like that, if you want to experience in virtual reality, you need to render both eyes, each at higher resolution and at 90 frames per second. And so that actually requires, if you multiply all those numbers out, is about 450 million pixels per second instead of 60. So it's roughly a 7x, 7 or more x improvement. And as displays get better and better, you'll expect that to go further. So we've been working on technology both in the GPU as well as algorithms to be able to bring down the cost of that by being smarter about the pixels that we draw. So the way that virtual reality works is there's a lens in the goggles that distorts the image to something such that when you move your eyes in any direction, it looks like it would be in the virtual world rather than seeing a flat screen in front of you. The consequence of that is that some portions of the image have too many pixels in them, and the other portions of the image have too few pixels in them. I think I did it backwards. Too few, too many. So one of the things that we implemented is an ability to do what's called multi-res shading. So you can now render the center of the image at really high resolution and the outer pieces at lower resolution, and effectively allowing you to either generate twice as much data or use half as much hardware to get the same effect. Another really interesting thing, since you're here at SIGGRAPH, you actually have a chance to see it live downstairs in the Emerging Technologies exhibit by NVIDIA Research. It's not a product, it's not a go out and buy it down the street, but it's what's called foveated virtual reality. And so it turns out that the human visual system only focuses on a very narrow portion of your field, and your peripheral vision, as you undoubtedly know, is is less sensitive, right? But when you've probably heard the notion of seeing something out of the corner of your eye. It turns out that the corner of your eye is sensitive to certain types of movement and certain types of things. And so there's a company called SMI that we've worked with that can track where your eyes are looking, and then we've developed technology or developed a bunch of human studies to understand how can you get away with rendering less in your peripheral vision without causing that to be a distraction. And it turns out if you only blur the periphery, if you only render it at lower resolution, it doesn't look good. But if you preserve contrast in a particular way that they've worked out, then you can actually get away with much lower resolution in the periphery, and it saves about 3x the rendering cost if you can track the eyes. And so that's a glimpse into the future. It turns out that if you really wanted to have a virtual reality experience that matches the fidelity of your human visual system, you would need over 100 times the number of pixels that we're able to deliver today. And so in order to be able to get there, we need techniques like this that we can make it practical. And then we've been working on technology to bring the photorealism to VR. So I told you it was really challenging. It needs 90 frames per second. It needs 450 megapixels, and my rendering takes minutes or hours. How am I going to ever experience that in VR? And so we've developed a technology called Iray VR. It leverages something called an idea called light fields, where you combine the fidelity of pre-rendering that you would get with Iray with an ability to view it in VR. And so there's two modes. One where you create panoramas that if you've experienced VR, you've probably seen that. But those don't feel quite natural because you're not allowed to move your head. It's like your head is stuck in a particular point. And humans are really good at understanding the spatial relationships of things by parallax, by moving our head back and forth to understand how far something away is, how large something is, whether something that's in front or behind. And so Iray VR gives you that very natural feeling of being able to move around in this immersive volume. And the way it works is we pre-render a number of light probes in that region, and then on a server, and then locally we rasterize a depth buffer at wherever the headset is, and then reconstruct an image from all of those light probe directions. And that's a hyper simplified version of what's actually a pretty complicated process. But it's because we do this, it's actually a very memory intensive thing. You can see some of this content in our booth. The boxes and the one on the right give you a sense of what we mean by an immersive volume. You can walk all the way down to the end of that tunnel, and all in full fidelity, global illumination, caustics, all of the very best rendering that we know how to do, and yet experience it in VR. So finally, AI. Artificial intelligence is going to change the world. It's already starting to change the world, and it will change the world in the next few years. It's changing almost every field. Computer vision was kind of the first wave, as I mentioned. People that have been working on algorithms to recognize objects and images for decades are suddenly surpassed by deep learning. And a slightly oversimplified way to think of deep learning is software that writes software. Right? By throwing a bunch of data at something, you can teach it how to recognize things, or teach it how to generate things of this type. And AI for graphics is actually a pretty big field. There's people. I just picked a few examples. People using it to simplify sketches. Right? You you teach it a bunch of sketches and then you show it a new sketch, and it knows how to remove extra lines in order to just extract the salient features. Same colorization, taking old black and white photos, adding color to it. There's a bunch of research on how to use deep learning to do that. And it uses, the neural network uses its experience that I know that, buildings are typically that color. I know that mountains are this color. And it's information that's not in the image, but it's in the experience of the deep learning thing. Style transfer is a really fun one. You can type in Google, real-time, not real-time, style transfer, and there's a bunch of websites where you can, upload a style like the Van Gogh painting. You can upload an image, and it will produce your image in that style. And it's not perfect, it generates some often hilarious outcomes, but it's actually really amazing what it can do. And we pulled out the SIGGRAPH proceedings this year, and it turns out that there's 18 by my count, maybe plus or minus a few, 18 different papers that employ deep learning in some form. And so I truly believe that this is going to revolutionize not just computer vision, but computer graphics. And I'll show you one more that I think is great news too. So this is what drives us to build stuff like this. Every single one of those things is an extremely resource-intensive operation. We announced this product yesterday, a Quadro P6000. It's faster and has twice as much memory as the one we announced the week before. And it has 3,800 cores, 24 gigabytes of GDDR memory, 12 teraflops of performance. And just to give you a little perspective of what that means. So in 2001, there was a computer called ASCII White installed at Lawrence Livermore National Lab, and it was 12.8 teraflops. And it cost $120 million. And I'm fudging it a little bit because this is only single precision performance, and ASCII White was double precision performance. But you'll forgive the factor of 2 for the difference between $110 million and the price of a high-end GPU. So this is, and it wasn't that long ago, right? And it's, our visual, the human visual system, whether you're creating images or understanding images, is incredibly complicated, and it takes that type of computing power to tap into it. And for many applications, that's not nearly enough. And so earlier this year, we announced the NVIDIA DGX1. It has 170 teraflops of FP16, 80 some odd teraflops of FP32, and 40 teraflops of double precision. So even on an apples-to-apples comparison, it would completely outperform that ASCII White machine by about a factor of 3. And it's an amazing machine. Of course, it's useful for more than just artificial intelligence. We've been using it for Iray and showing that it's faster if you have a little bit of data, but if you have a lot of data, it's even faster. And that's because we've architected the whole thing to be able to have massive throughput on large amounts of data. And of course, it's not just the hardware. We invest a lot in software. So if you're a developer, I'd encourage you to check out the NVIDIA SDK for all sorts of topics. One of the most relevant is a section of that we call DesignWorks, that for ray tracing, for processing video, for virtual reality. We announced several updates to that this week, and that you'll like to, I'd encourage you to check out. One of the interesting ones is VRWorks 360 video. So you take multiple 4K video streams and ingest it, stitch them together into a 360-degree panorama, and stream it out. And it can do that in real time. So it's ingesting several video streams, not They can be 4K or there can be 32. They can't be 4K and 32, but we'll get there. And stitch them together. And it's, it does so in about 3 or 4 frames of latency. So it's a really useful tool for generating content live. And I'm just picking a couple of these that are interesting. GVDB is kind of the GPU equivalent to a very successful, very amazing product called OpenVDB that was created by Ken Museth at DreamWorks and also works at SpaceX. And it allows you to very efficiently use sparse volume, so you can generate massive meshes. This is actually a voxelized image. Very dramatic, roughly 2 billion voxels in that case and represent them efficiently. Optix, our ray tracing API, has some great performance benefits, ability to ray trace almost 800 million rays a second in some cases, over 500 million rays per second of ray tracing, and a lot of benchmarks. And one of the things that's been fun is to combine the DGX-1 with ray tracing. And so DGX-1 has a technology called NVLink that connects the GPUs to get on the system together at about 80 gigabytes per second. Using NVLink and DGX-1 and Optix and a whole bunch of typing from my Optix engineers, we can scale, render a scene interactively up to about 64 gigabytes of data. And so we're showing this on some data courtesy of Pixar from Monsters University that has about 130 million polygons, tens of millions of blades of grass, several 15 to 20 gigabytes of texture, all of which are ray traced, and it's amazingly fast. I'd love for you to stop by and check it out. So so how are these useful? Well, it turns out we actually eat our own dog food in a lot of our own designs. So this is the NVIDIA Shield product, and we actually used Iray to help design it. One of the most challenging things to design on a product like this is the light pipe. Light pipe takes 1 or 2 LEDs and tries to make something really broad that like this thing here. And there's a plastic waveguide that's used to illuminate that, and it's really a trial and error process because it's hard to understand how light bounces around in these waveguides. And so the design team was able to use Iray to turn what was originally on the left a bad design that shined light out of one direction and not the other into something without increasing the manufacturing cost. And then we're also using it for designing our own building. NVIDIA is building a new headquarters. We have 9,500 employees running out of room. We can't stack them on top of each other. And so we're building a new several 100,000 square foot headquarters shaped like a triangle. And but we're simulating what it would look like, how would it feel, how would it function before we invest in it. And so it's actually now under construction, but these are images from a few years ago where we're studying how light enters the building. We're still looking at what materials we want to use, and you can actually experience in VR. If you search for Iray VR NVIDIA Campus in the Google App Store, you'll probably find it, and you can load your phone into a Google Cardboard and click through a number of things that our building should look like in the near future. And then as we're building it, we're actually flying a drone over it every single day and reconstructing photogrammetry from the building. So, and we also have that data downstairs, and you can thumb through on a day-by-day basis. You see the buildings that used to be there get destroyed in about 2 days, and then the framework built up, and now the roof. And I think the image below is from less than a week ago. But you can, it's a point cloud data that we gather every single day, and I haven't experienced myself, but my understanding is you can actually now stand on top of the building in real scale, which I don't, so certainly one of those don't try this at home things. The in laser scans for the interior of the building as well helps us understand what's being built, and maybe at some point in the future, if we need to know, is there some wire behind this wall, it'll come in handy. But it's not just for generating pictures or understanding what's built. We actually used it to simulate the levels of light. So this was an early design of the way the roof, and we wanted to understand this building plays a lot on natural light, and tries to make it so you don't have to turn the lights on most of the years. Northern California, why do you want to have walls and artificial lights, right? But in order to use sunlight, it has to be you have to be delicate with it, otherwise it gets too hot or too much glare. And so this was an early design that we actually showed was going to be way too much glare, and resulted in some design changes. And so, on 9 a.m. of, I think this was the fall equinox or something, on 9 a.m. of the fall equinox on a typical Northern California day, using data from the local weather station, we would have 1600 lux on this particular desk. And so, we heard about this building. We thought it'd be fun to use that. So we heard about this building in London. It's called the Walkie-Talkie Building, or it's called the Death Ray Building, because for about 2 weeks a year, it's convex in two directions, and it turns out to focus light on a particular street. And nobody believed that this was the building until some guy parked his Jaguar there, and it melted the Jaguar, and melted some plastic piece on the side of it, and so we thought, well, let's see if we could simulate that. And so we modeled the building, we modeled the surrounding, and it's actually a caustic, so it's a very difficult to simulate, very computationally intensive, but showed that sure enough, in some cases it could reach 170 degrees Fahrenheit. I don't remember the Celsius conversion, and in fact, what hadn't been realized, it makes sense if you think about it, but what they never realized is that this effect can actually happen twice a year, and the problem, once in the fall, which they knew about, and once in the spring, which reportedly the sun never comes out in the spring anyway, so it's not a problem. So this is ground level view. I don't think that's actually a Jaguar, but I think the effect happens on all makes and models of cars, and computed the radiative heat transfer, made a few assumptions, and derived what the heat value is. So those are some examples of what I mean by combining simulation and VR and things like that. There's a bunch more that we're showing off downstairs. I want to give a nod out to another one that since I'm an Autodesk thing, Autodesk is working on to combine a bunch of these things, called Dreamcatcher, and a related project called Design Graph, where they're combining a lot of these elements to simulate designs and optimize those designs. And it really combines all of those elements. Another great example, it's called generative design, where have the computer design it. You just tell it, I want some wheels and I need it to hold up a certain amount of weight, and let the computer run with it. And another nod to another great project that's derived from that, called HackRod, where they're taking that one step further and actually creating a race that uses all of that latest technology and advances, and artificial intelligence, simulation, even some VR and rendering, in order to change the way that vehicles were designed in the future, similar to the way that racing really helped the automotive industry evolve in the last century. So that's what I mean. That's what NVIDIA means when we say visual computing. It's not just one thing. It's not just flops. It's not just generating pictures faster. But it's really the melding of all those things together. You're not solving one problem at a time. You're solving all of those problems. You need your AI to work with your graphics, and Dreamcatcher generates complicated designs, and so you need better graphics, and and you need more horsepower to compute more sophisticated designs, and you need VR to be able to understand those things and to communicate them. You need rendering because that's our world has global illumination in it, and so our visual system is really good at understanding global illumination. And so all of those things combined together, that's really what we mean when we say visual computing. And so that's why when we say visual computing is our singular mission. NVIDIA is really not focused on anything else. If it's whether it's the smallest thing we make, Tegra 10-watt thing that goes in a self-driving car, all the way to a 170 teraflop DGX1, all of those things are driving us to build this idea of visual computing. And that's all I have. Thank you.